motion being dropped at rest, the observed motion will be measured and then compared to two different computational models to see the difference of how knowing the forces gravity and drag can affect an object's position and how they will predict the motion observed. The result outcome is that more forces taken into consideration, the more accurate the predicted model will become. This is proven by the fact that there is less deviation in the observed model and the model that includes the drag force. Newton's second law states that the forces applied on a system when there are interactions between objects. All these interactions can be added up to equal one net force, which can be measured as a change in momentum over a change in time. In this lab, an object is being dropped from rest. Since the initial velocity of the object is 0, but then speeds up, this indicates that there is an acceleration and a non-zero net force acting on the object due to the momentum principle. One of these forces being gravity, or the force of the Earth on the object. The gravitational force, or the weight force, is proportional to the object's mass and has a specific constant known as Earth's gravitational force, which is also known as 9.8 newtons per kilogram. This constant comes from the gravitational law. This number is negative in the y direction since the object is falling towards the Earth. In the first computational model, we only took into account the force of gravity on the object. Therefore, the net force is only equal to the gravitational equation described before. The deviation on this graph indicates that we are still missing a force in our predicted value. The atmosphere is made up of many particles, and these particles will have interactions with falling objects. These interactions result in the drag force. The larger the surface area of the object, the larger the drag force. The drag force is proportional to the square of the object's speed times some proportionality constant. You must remember that the drag force will be pushing against the falling object, so the value needs to be in the opposite direction of the velocity vector. With these two forces added together, the net force of the object can be calculated. As you can see, the deviation between the object's observed force and the predicted model where the drag force is included is much smaller than before. This goes to prove that the drag force does play an important role in the predicted motion of a falling object. While there is still discrepancies in this graph compared to the observed motion graph, this could have been due to countless things, such as wind in the air or other outside environmental forces not taken into account during this lab. When looking at velocity graphs for the two predicted models, the one including drag force began to reach non-zero acceleration, a zero slope in the velocity graph as seen here. This indicates that there is a specific speed that cannot be exceeded. This is known as terminal velocity. At high velocities, the force of air becomes just as great as the gravitational force, and a constant velocity is reached. Even when an object is being thrown downward, comparing to starting with no initial velocity, the object's velocity still reaches a terminal velocity. In this case, terminal velocity is just reached quicker than when the object starts at rest. This was tested in glow strips by starting the ball with an initial velocity of -1, and as you can see, the slope still bellows out to a zero velocity slope.